Hey guys, Mr. Betts here. In this video, I want to introduce you to an anti-differentiation method called integration by parts. So if you remember, all of our anti-differentiation rules come from differentiation rules. We don't have a general method of finding antiderivatives like we did with derivatives using that limit definition. So with antiderivatives, we have our derivative rules and then we work backwards from there. Integration by parts is the rule that we're going to use for antiderivatives that reverses the power rule. So if we get a derivative that we would have gotten using the power rule, then we can get its antiderivative using integration by parts. And the formula that we're going to use for integration by parts comes directly from the power rule. So if we take the power rule, which is on the screen here, and then we take the antiderivative of both sides with respect to x, then what happens here with a little algebraic manipulation on the right side, we're going to have dx's cancel. Antiderivative here is just going to be u times v. Over here, dx's cancel, and we have the antiderivative of v with respect to u plus the antiderivative of u with respect to v. And then solving for this one, just because that's the form that the formula is in, we get the antiderivative of u with respect to v is equal to u times v minus the antiderivative of v du. Now, this won't mean anything to you yet, but this formula right here is a way that we can use a version of substitution, but instead of substitution just choosing a u and then making substitutions in terms of u alone, we're going to choose a u and a dv, and we're going to be able to use this formula then to evaluate an antiderivative. So I want to take a look at a specific example and show you how that's going to work. So in this particular example, what I want to do here is I want to choose a u that I'm going to end up taking the derivative of, and I want to choose a dv that I'm going to take the antiderivative of to get v. So I'm going to choose u to be x, and I'm going to choose dv to be sine of x. It's not going to be obvious at first why we make those choices, and I'll talk more about how we're going to make our choices later. I do want to point out that this entire thing here has to be dv, and this right here is going to be u, because our integral to start with needs to be u times dv. So dv is going to be sine of x dx. So then the next step, in order to use this formula, we need the derivative of u, which in this case is just dx, and we need the antiderivative of dv. So to get sine, we take the derivative of the opposite of cosine of x. And when we take the antiderivative, we can get rid of the dx. And there is a plus c on here. We don't need the plus c at this point, but technically it is there. And so at this point, it's just a matter of plugging into this formula up here. So this expression, this integral, is going to be equal to u times v. So it's going to be x times the opposite of cosine of x minus the antiderivative of v du. So v is negative cosine of x, and then du is equal to dx. Now, notice that we still have an integral in our expression. However, where we had a product up here in our integrand, now we just have cosine of x. And that is an antiderivative that we can evaluate very easily. So we have negative x cosine of x. And then we take the derivative of sine to get cosine. So it's going to be plus sine of x. And at this point, when I take the antiderivative of this, I need my plus c. I did not need it before. Remember, I mentioned that technically there's a plus c there, which would mean that there's a plus c here. I don't need it though, because this plus c that I get with this antiderivative and this plus c here together are a constant. So the plus c built into this one takes care of this one for us also. Okay, so we don't need the plus c until we take our final antiderivative, and we get that right there. Now, it's not a bad idea anytime you take an antiderivative to take the derivative and make sure that it works. And when we take the derivative, notice that we would use the product rule here. I'm not going to go through those steps, but we would use the product rule there, and we'd had some canceling, and we do end up with x times sine of x as our derivative. So let's think about what we want to do when we're making our choices for u and dv. So we're going to choose in our expression, in our integrand, something for u that we're going to take the derivative of, and something for dv that we're going to take the antiderivative of. So first of all, we need to choose something for dv that we can take the antiderivative of. We don't want to have something in there for dv that is something that we can't take the antiderivative of. Because remember, things like sine of x squared is not something we can take the antiderivative of. So it would be a bad choice for dv. So something we can take the antiderivative of, and when we do, we don't want the expression to get more complicated. So taking the antiderivative of dv should not make the expression more complicated if we can avoid it. There are some specific situations where we might not be able to avoid it. When we choose u, remember we're going to be taking the derivative of u. So when we choose our u, we're going to end up using du. And so when we choose u, we want to take the derivative, and we want that derivative to get simpler. Because when we take the derivative of du, it's still going to be involved in an integral expression. And if it doesn't get any simpler, then this choice isn't going to help us to evaluate the new expression. So some special cases, if the integrand involves something that we don't know the antiderivative of, that has to be u. So I mentioned this already. We can't choose dv to be something that we cannot take the antiderivative of. So if we have a logarithm, if we have an inverse trig function, those things we can't take the antiderivative of. And if we do take the antiderivative of those, they actually are pretty complicated. So we want to be able to take the derivative of those things. So if you see a natural log, if you see an arctangent, that's usually going to be your u, and then what's remaining will be your dv.